Hello, this is going to be a quick tutorial on how to generate patterns using the SV5C. The tutorial will be targeted towards doing DDR patterns, but it will apply to the more general case as well. So the first thing that we're going to go over is we're going to start from the basics, and we're going to look at the user pattern. So the user pattern in the software is the basic building block for all pattern generation. And really what it is in the end is just a storage type for a sequence of bits. So you would add it from the menu here like you would any other component in the software. You would locate the user pattern and you would say add component. After you've added it, you'll see the menu that pops up on the right here, and there's a few different fields. The ones that are grayed out here are things that are auto-filled when you add stuff into the bits field. So here is what is the bulk of the pattern here. This is where you'd add the specific bit sequence that you want to send, and you just type it in. It'll give you information at the bottom of how many bits you've added, and this is modified in real time, so you can see it as soon as you type something in. And you also have the transition density and the mark density at the bottom. Once you add the number of bits here and you press OK, then the other fields at the bottom will fill out and you'll be able to see a final bit count that you've added. And then as well here at the bottom, there's something called the storage bytes. Now, what this tells you really is just how this pattern will be stored in memory. And our internal structure is to use a 512-bit sequence for all pattern storage. So when you add a number of user pattern bits here, it's going to be padded up to a multiple of 512 bits. Normally what happens if you just leave the default is that it will be padded by concatenating the pattern onto itself so that you get a longer pattern which has the same bit sequence, but you can also specify a padding pattern and that will be used instead to pad it. So if I were to have my 8 bits here of 0101, and I added a padding pattern which was all zeros, then it would put my 8-bit sequence and then it would follow that by all zeros until it reached 512 bits. Now, it will never cut your pattern in half. It will always concatenate a whole multiple of the number of bits that you added. So if I add a pattern that has 9 bits instead of 8, then you can see that it will have a very large number of storage bits, and this is what the device uses to play the pattern. Now, for just using user patterns as they are, which is the most basic way to do pattern generation, it doesn't actually matter that much what your number of storage bytes is, because your pattern is going to play in an infinite loop anyways. So if I use using my TX channel list, if I just assign a user pattern to the channels, then when I do TX channel list.setup, it's going to start playing this pattern and it will just keep playing the same pattern until I either change the pattern or I call a txchannellist.stop patterns. Now, when I do a txchannellist.update, it will also change the pattern if I have modified the pattern field here. So you can either set the pattern at the component level or you can set it in your program. But if I were to change my pattern after this sequence here, so I take this and let's say I had a user pattern 2, I could do this and I would say update instead of setup, and then now it will, instead of resetting up all of the parameters with the TX channel list, it's only going to change the pattern. So you can change it to user pattern 2 and then you click update and it'll change your pattern, and that will stop the previous loop and start a new pattern loop. Now, when you call txchannellist.stop patterns, you enter into what we call a hold pattern state. So that's going to be the next part of this tutorial here. So this next section of code, I just demonstrate really quickly how to use the hold pattern states. But basically what this specific pattern state is it's used during any transition between two regular patterns, or if you call stop patterns. So normally we'll be playing from a user pattern or a pattern timeline or a pattern sequence. Anytime we're either changing between two user patterns or two other types of patterns, there's a period where pattern bits will be written to the internal memory on the device, and in order to prevent any corruption at the output, we switch over to the hold pattern states. There's three options for the hold pattern states. The first is very basic, and it's idle. The important thing to note about this is idle here means electrical idle, so your output would be floating, and it does not mean a protocol type of idle. So it's actually no pattern bits are being played. Your transmitter is held in electrical idle. The other two options are these Alt-A and Alt-B patterns. So these are, you can think of them as just separate pattern memories that are independent from our larger and general user pattern memory. And these can be played in place of the user pattern memory when we're transitioning between two patterns. You can also use them in the pattern timeline, which we'll get into a bit later. You set the bits for these in the TX channel list, and if you have multiple TX channel lists in your test procedure, you should note that the Alt-A and the Alt-B bits are global. So if I set it in one TX channel list, whatever setting I have there is going to be ported over to the other channel list as well. So you don't actually have 4 different options. You have 2 different options, no matter how many TX channel lists you have. So for this example, I've set my Alt-A bits to be an all ones pattern, and I've set my Alt-B bits to be a toggling clock pattern. Now these Alt-A and Alt-B bits have the same properties as the user patterns in that they will pad up to a multiple of 512 bits, and they will also play in a loop as long as they are selected. So whenever we're in a hold pattern state and we're playing Alt-B, it's going to be looping over the Alt-B bits infinitely until there's some other change that happens and we maybe switch back to our user patterns. So this example here is just setting the hold pattern states on the channel. I call an update, which will change whatever the hold pattern state is, and it will also resend the Alt-A and the Alt-B bits. So it's going to reprogram those. And when I call TX channel list.stop patterns, then my transmitters are going to switch over to playing those pattern bits. So if you were to run this sequence, as soon as you click stop patterns, you would see that now you've got an all ones pattern and a toggling clock pattern on your channels. The next part of the tutorial is going to be about the pattern timeline. So the pattern timeline is what we use to build more complex sequences of patterns, and it's also helpful if you want to do something something like play a pattern once and then switch over to another pattern, or play a pattern once and then go over to whatever your hold state is. You just have more control over it this way, and you also have specifically you have more control over the number of bits that are being played. So if you had a long sequence of patterns, if you would set those up as user patterns and you would play them consecutively, then you would end up with more bits than your actual desired pattern length because of the padding and because of the fact that you have to switch between the patterns asynchronously from your test procedure. But this way you can set up a whole sequence of transitions, and the patterns will still be padded, but instead of being padded as individual patterns, they are padded as a whole sequence. So we concatenate all of the bits from the different patterns in the pattern timeline, and then the padding happens at the end. And you can control which part of the pattern sequence is padded. The easiest way to figure out what is happening and where the padding is occurring in your pattern timeline is to use the wizard. So we have the code for the timeline that appears here. And we also have in the list view here, so this is the main window that pops up when you click on the pattern timeline component. You can here use this to add different patterns. So in this example here, I have a K28.5 pattern and a div16 pattern, followed by a clock pattern, and then ending with my Alt-B. So this Alt-B pattern is the same Alt-B that's used in my hold state and the same bits that I set up in my TX channel list. So I can add this hold state pattern, essentially. I can add those bits to my pattern timeline and have that play at the end. So one thing with the pattern timeline that's important to note is that there's a special parameter on the bottom. So when you add a new pattern, you see a little checkbox that's called flexible. And what this does when you click it is it's telling the software that if there's going to be any padding of the pattern, it should happen on this entry. So these other two here, I didn't put that setting. I put it on this last one here, my clock pattern, because my clock pattern is the same as my Alt-B, which is the same as my hold state at the end. So I don't care if it adds any extra bits of this clock pattern here, because I know that I'm going to have, I'm going to play these two patterns once, and I want an exact number of bits. And then I would transition to this, and because it's the same as my Alt-B pattern and my hold state, you wouldn't even notice if it padded any of the bits there. In order to figure out if you got what you desired when you added all of these things to your pattern timeline, you can go over to the Reports tab, and it'll tell you the number of UI that you requested from the pattern. So here I specified them in number of pattern lengths. I said 1 pattern length. And the first pattern is a 20-bit pattern, and the second one is a 16-bit pattern. So those are my 2 requested UIs. It tells you the achieved number of UIs. So this is after any padding has occurred in order to store the pattern. So when I put flexible equals true on the last one, it duplicated the number of pattern bits here. So I went from 16, sorry, not quite a duplication, but I went from 16 UI to 28 UI. And these two here, because I didn't put flexible there, I got the exact number of bits that I achieved. Now, if I were to not put flexible on this sequence here, then the software will decide what it wants to pad, and it actually padded every pattern individually. So instead of getting 20 UI, I got 25. Instead of getting 16, I got 20, and then with the last one, I got 19 UI. So this wouldn't be the sequence that I would want, because what I actually wanted was 20, 16, and then these are all don't care for number UI because it's the same pattern. So it's important to always add a entry at the end of your pattern timeline that has the same bits as your Alt-B pattern or your end with pattern. And your end with pattern, which is the final one that it plays here and it will loop infinitely, this pattern should be the same as your hold state. Now, this is something that will generally apply to most cases of DDR pattern generation, but can also be more general than this. But really what this does, this setup, is it ensures that you have clean transitions between your 2 separate pattern timelines or your pattern timeline and whatever user pattern you play after. And it also ensures that you're getting the exact number of bit sequences. So if instead of a K28.5, this was an MRR or an MRW command in DDR5, I would not want it to repeat that command. I would want it to play once. So the example that I have here is I have 2 different pattern timelines, and I'm going to transition from the first pattern timeline on channel 2 to the second pattern timeline on channel 2. And I've got a little timeline generated here to show you what the sequence of events is going to look like. And I've done this setup with the same principles that I just mentioned, using the hold pattern state and having the same bits as the hold pattern state in my final end with pattern in the pattern timeline, and also having an entry at the end of the timeline which has the same pattern bits again as the hold pattern state, and then putting the flexible option on that. So this is the sequence that you end up with here. You got your K28.5 playing 20 bits once, the div 16, which is 16 bits, and then you transition into your clock pattern here. And this pattern will hold from the end with pattern into your hold pattern state when you call the next TX channel list setup. So your TX channel list update to start playing the second pattern timeline happens somewhere during the period where this clock pattern is playing. But while your new pattern is being programmed into memory, your output will not be disturbed. So it will always play the clock pattern in between. And then after, once the pattern is stored in memory, it's going to transition from the hold pattern state, which is your clock pattern, to a div 20 for 20 bits, and then a K28.5 for 20 bits, which is my second pattern timeline here. And then I did the same thing with my second pattern timeline. I have an end with Alt-B pattern, and I have my clock pattern as a flexible. So once it's done playing the K28.5 for 20 bits, it's going to transition into the clock pattern again. Now the next example is essentially the same thing as using pattern timelines, but it's kind of a wrapper on top of pattern timelines that allows you to, instead of specifying a pattern timeline for each channel indexed by the channel numbers, so setting a list of pattern timelines here in the channel list, you can use, it's this one. So normally in regular mode, you would specify a list of the pattern timelines here in your channel list, and you would put one for each channel number you have. When you use the bus pattern timeline component, it allows you to specify a dictionary of pattern timelines that are indexed by channel label. So this is helpful. This is helpful for DDR applications because you would really be referencing everything and building all of your patterns with respect to whatever the channel function is rather than the channel number. So the first thing that you have to do to set up this type of mode is to add a label component. So there's a generic label component that you can use in the advanced menu here, the TX channel labels. But we also have on the SV5 ones that are pre-built for DDR applications. So the one that I'm using this example is the RCD channel labels. And I would add this to my test procedure like I have here. And that way I can assign a channel number to each of my DDR signals. So my clock channel is going to be my first one in this example, and then I have my reset, the chip selects, and the command address pins. I would add this to my channel list here. So at the very bottom, there's a channel labels field, and you would add your DDR RCD channel labels here. You also have to add your labels to the bus timeline component. So once you declare a bus pattern timeline, you set the labels for it, and that way when you build your pattern sequences, it'll assign the correct pattern to the correct channel based on the label. So the easiest way to set up a pattern with the bus pattern timeline, or the simplest way, I guess, is to create a dictionary of user patterns indexed by label. So that's the example that I have here. So you would create some kind of dictionary and you assign bits to each of the labels in here. You can also assign user patterns. So I could put my user pattern 1 in place of the 0, 0 here. And you can use any of the prefabbed user patterns as well. And then once I've created this dictionary of patterns, I would attach that to my bus pattern timeline as an entry. So that's the same thing as adding an entry into here. But now instead of adding an individual pattern, I'm adding a dictionary of patterns. And each of these patterns will get the duration that I've requested and the type or the duration mode. So here I want to play these patterns for 20 nanoseconds. And based on what I put in here, it's going to calculate a number of bits that are required. And you can use the same method for building your pattern timelines as well. Instead of using the component, you can declare them right into your test procedure. But it's often helpful to use the component, at least for an initial stage where you're planning out what your pattern timeline is going to be, because then you have access to the reports tab and you can see exactly what it's generating. As with my other pattern timeline, I've got an entry at the end here where I put flexible equal true. And this is just a pattern that I don't mind if it pads. And then I've got my final entry here, which is the end with patterns. So these I've actually put in my Alt A and Alt B states. And for my clock channel here, you can see that there's a different one. All the other channels are using Alt A, which is my all ones pattern. But my clock channel is using, of course, the clock pattern as the hold pattern state and the end with pattern state. In my channel list here, this is where I set what the hold pattern states were. So I've got Alt B for the clock channel, which is channel number 1, and then I've got Alt A for all of the following channels after that. So with the bus pattern timeline, instead of setting your txchannellist.channels property, you do txchannellist.setBusPattern timeline, and then you add in the bus timeline component here. And you also have to set your channel list to use the bus patterns mode. So here in the TX channel list, there's pattern mode. So the standard, that's where we would just add the user patterns. as a list, and then the bus patterns, you get a new field here called bus pattern timeline, which replaces the patterns field, and that's where you can add your bus timeline. And now you're assigning a single object to that field instead of having a list. So one of the applications for DDR using the bus pattern timeline uses another component that we have called the command pattern component. So we have a RCD1, a DRAM1, and a DB1. And really what this does is it generates a dictionary of user patterns indexed by labels. So using the same labels as the RCD channel labels or whatever other labels you're using. So you set that on your pattern timeline. And you would set the RCD channel labels if you're going to be using the DDR RCD command pattern. And then you can use this component. There's functions attached to it, and you use this to essentially build a user pattern. So this doesn't actually build the pattern timeline for you. You still have to do that after using the bus pattern timeline. But this way you can set up a sequence of commands, and it will generate all of the bits necessary for that. So it's really just a more user-friendly way of generating sequences of mode register writes or mode register reads or deselects, and then you can set properties at the beginning, like the chip select levels, whether or not you want it to be double data rate, and these will apply to all of the commands that you add after. So here the sequence that I have is just kind of a arbitrary snippet that I took from a test that we have, but I'm just setting up for the LFSR DFE training mode. So I'm setting the seed on 3 of the LFSR registers on 3 of the command address pins, and then I configure the DFE training mode at the end, which is another MRW command. And once I've finished generating the sequence that I want, and you can make this as long as you want, and you can also use different command pattern components. So in this example, I actually have 2. I have one that's my DDR RCD command pattern 1, and then I have a command pattern deselect. These are the same component, but I'm just using them to generate 2 separate patterns. So one of them is just going to be a deselect pattern. So once I'm done building the sequence here, I go compile patterns, and this is what returns the dictionary of user patterns. You can also build a report, and that will show you the exact bit sequences that you're getting from all of the commands that you did above. So I've got that printed out in the log here, but this is what the report looks like. So after I've added all of my deselects and my MRWs, you can see it'll print out all of the bits required for these operations, and you can check to make sure that that's exactly what you got. You can't modify them from here, but if something is incorrect, then chances are something is wrong in the declaration of the function that you used here. The deselect command pattern that I added is just simple. It does one single command. And the only reason that I added this is so that I could add it at the end of my pattern timeline as my in with pattern, and then also as above, add the deselect pattern, which is something I don't care if it pads, as a final entry before the end with pattern, and set flexible equals true. So what this sequence is going to do is it's going to go through all of these commands here, the MRWs, and then it's going to go into deselect, and it'll keep playing the deselect. So with the clock toggling, the reset high, and the command address are don't care in this state, but we set them to all zeros. And then that's going to be my whole bus timeline for that. So it's going to play all of these commands once and then transition into a deselect. And then what I do finally, so this is another way to do it. Up here, I used a function, set bus pattern timeline, but you get the same effect down here. I just did tx channel as 2 dot bus pattern timeline equals bus timeline, which is what I set up here. And then I do my setup. So this example at the bottom here kind of combines a lot of the different things that I talked about in the tutorial, but this is what will be the most helpful for anybody doing DDR. Something like we've got here, you might want to use this if you're just doing a reset sequence for a DDR application, because you can specify different sequences here, and you're not actually sending any commands at this point because it's just during initialization. So it's easier to do the patterns in bits like this. And then once you've got through the initialization sequence and you're doing, and you've got past any training or even during the training, you can use the command pattern component to build command sequences. All right, that's all for this tutorial. So this code will be available, and there's a lot of comments in this as well that kind of repeat a lot of the things that I said in this, but it is here as a reference for anyone that's using DDR patterns or anybody that is curious about how to use the pattern timeline in our software. Thank you.